In this lecture, we're going to cover nucleophilic substitution, or the SN2 reaction. Before we get into detail about the SN2 reaction, let's look at nucleophilic substitution reactions in general. In these reactions, you can see that we have a nucleophile. Remember that a nucleophile is nucleus-loving or electron-rich, and we have a reaction with a leaving group. In this case, the electron-rich nucleophile is going to displace the leaving group. And the nucleophile can be negatively charged, and in that case, the product will be neutral. Or the nucleophile can be electron-rich and neutral, and in which case the product will have a positive charge. In both of these examples of nucleophilic substitution reactions, we have a charge balance. So if the nucleophile is negatively charged, then the leaving group will come off negatively charged. And if the nucleophile is neutral, the resulting positive charge is balanced by the negative charge on the leaving group. The best leaving groups will be weak bases once they come off in the negatively charged form, as you're seeing here. Weak bases are stable, and we want our leaving group to be more stable than the incoming nucleophiles. Nucleophiles, on the other hand, are going to be electron-rich. Let's look at some examples of substitution reactions. Specifically, we're going to look at the biomolecular nucleophilic substitution, or SN2 reaction. In this reaction, the S stands for substitution, the N stands for nucleophilic, and the 2 stands for biomolecular. Biomolecular means that 2 molecules are involved. In this case, you can see that we have a nucleophile and a substrate. Here we can see the nucleophile, the electron-rich part of the reaction, going to the electron-poor substrate. Remember that the substrate is going to have a delta plus on the carbon and a delta minus on the chlorine. And so we have our arrows going from electron-rich to electron-poor. The arrow is showing the lone pair on the nucleophile that I've drawn in red here, forming an oxygen-carbon bond. And I'll draw this in on the right. So this red lone pair is becoming an oxygen-carbon bond. At the same time the oxygen-carbon bond is forming, the carbon-chlorine bond here in blue is going to break and become a lone pair on the chlorine. So the red carbon-chlorine bond becomes a lone pair on the chlorine. Again, what we're doing here is we're doing a substitution reaction where the nucleophile, the electron-rich nucleophile, forms a bond to the electron-poor substrate. The leaving group falls off, forming a weak base. And all of this happens at once. Let's look at one more example. In this case, our nucleophile is ammonia, an amine, and it's neutral. But remember that amines have a big delta minus because of that lone pair. So the delta minus now, or electron-rich portion, is that lone pair, drawn in red here, going to form a nitrogen-carbon bond. So the red lone pair becomes the nitrogen-carbon bond. At the same time, the carbon-oxygen bond breaks, and those electrons go to the oxygen. The oxygen-carbon bond breaks and becomes a lone pair on the oxygen. Again, we are going from the electron-rich nucleophile to the electron-poor carbon. There's a delta plus on the carbon because the oxygen is more polar. So the delta plus is on the carbon and the delta minus is on the oxygen. The resulting leaving group is a weak base. And if you are trying to remember why this is a weak base, keep in mind that the negative charge in the oxygen is stabilized by resonance. You can push that negative charge up onto the O here or down onto this O here. On the top, our leaving group is a Cl minus. It is also a weak base because chlorine is electronegative and can handle that negative charge nicely. Let's look at this animation of a nucleophilic substitution reaction so you can get a visual idea of how this works. In this SN2 reaction, the Br minus is the nucleophile, and it's going to come in and form a bromine carbon bond, shown here, and at the same time the carbon chlorine bond is going to break, releasing Cl minus. Let's zoom in and see how this animation works. You can see the arrows here that we're going to follow, and now watch the bromine in red come in and the green, Cl, falls off. Again, the Br comes in and the Cl comes off.